All right. Good thing. Today is our third lecture, which is probably for the second. My plan for today is as follows. So what I want to start with, I want to discuss briefly what the demand function is, because this is kind of the most important tool for you to know as managers. It's kind of knowing the best about your opponents. Thinking about it as opponents. I mean, these are the correct way. About the demand briefly, and then we'll switch to the computers and we'll try to estimate demand from a data set. And I'm going to show you basically I created a practical guide to a linear regression. So I'm not going to spend a lot of time talking about the assumptions of a linear regression, what exactly it's trying to perform. It's going to be practical in the sense that I want to show you how it works in practice. And my approach there is it's helpful, you should use it, even if the basic statistical assumptions of the method are violated. And if it's not helpful, I'll try to find something that works better. But before we do so, let's talk about the demand function. You've probably seen it before, or at least you've read about it in newspapers because journalists are not afraid to use this stuff. But basically, the picture that you have when it comes to the demand function is just a picture of a downward sloping line, something like this, right? And we will need to be careful with respect to maybe like demand. Once you go to the bottom, the problem with this description is that if you are taking math class, the independent variable usually goes on the bottom, right? The exponents are variables here, and then what's being explained goes in the vertical axis. The economists have it flipped. There are historical reasons for doing so. I'm not going to talk about historical reasons, but the only justification that I can think about, it's really, like, practically speaking, it's really convenient to talk about price levels. So the price level goes down, that means the price increases. Price level goes up, that means the price goes up. But price is the explanatory variable when we talk about demand. In a nutshell, the demand function is just a relationship between price and quantity demanded. Basically, think about a particular market, think about a particular product, and I'm going to give you different prices. And for these different prices, the demand relationship tells me how many units of the product buyers will be willing to buy at that price. This is the standard definition of demand. So, for example, I could say, well, if the price is $10 per unit, buyers will be willing to buy 50 units. If the price goes down, say, $9 per unit, buyers will be willing to buy 60 units. So this is the standard definition of demand. Given the price, how many units will be demanded at that price? Now, I have to emphasize that this relationship is hypothetical, because when we're looking at real markets, we don't have the privilege of asking the buyers, if I were to play around with prices, what is the quantity that you will be willing to buy from me? So we have to infer it from some kind of back road and trying to find out what that relationship is, even though the consumers are not giving us the full information about their willingness to pay at different prices. The second interpretation of the demand function. So right now, the way I'm reading this table is just like I explained to you. Price is the independent variable. I'm feeding you the price. The demand function spits out what quantity that price corresponds to. But there is also a second built-in interpretation of what the demand is. Think about this. If the price is 10, I can sell 15 units in the market. How much do I need to bring the price down to sell the 16th unit? $1, right? So I need to charge 9. So that means that buyers are not willing to pay more than 9 for the 16th unit. So you can think about the demand also as representative of willingness to pay for each additional unit. On the one hand, it represents, well, the standard relationship between price and quantity, but second, Demand simply stands for the marginal benefit of consumption, or alternatively for the willingness to pay for each additional unit. And this thing is sometimes abbreviated as WTP, willingness to pay. For each additional unit. Now, in my example here, to sell the 16th unit, you need to bring the price down to 9. So the 16th unit is only valued at $9 from the buyer's viewpoint. They're not going to pay 10 for it. They're going to pay 10 for the 15th unit, for example. So I can write down that the marginal benefit of the 10th unit is, sorry, not 10th unit, 16th unit, $9. Right? And so in this way, going to the right in terms of quantity, every time I increase quantity, I can tell you how much people are willing to pay for this additional unit. Like the marginal benefit of consumption, the willingness to pay for extra unit. So this is the second interpretation that's often overlooked, but it kind of matches the idea that the supply represents the marginal cost of production. So the supply represents your additional costs of producing an incremental unit, which I'm not going to touch on right now, but I mean, if you ever thought about the supply, this is what it does. Demand represents additional benefit to consumption. And this additional interpretation, well, sometimes it's useful. And so we have this thing, which is called the law of demand. I'm going to write it down here. The law of demand simply says that this relationship has to be negative. Your demand picture has always must always be a downward sloping curve. If you reduce the price and you're selling less, something's wrong. If you increase price and by increasing price you're able to sell more, something's wrong. That's not a typical demand behavior. Maybe it's possible that in some markets this is how things work, but typical behavior of demand, bring down the price, quantity demanded increases. Now, the law of demand comes with a huge asterisk, with a huge price tag. We can't just look at price and quantity in isolation. So the law of demand, if I want to be more careful, says that this relationship is negative, other things being equal. So here. The relation between price and quantity demanded. Well, I can say other things being equal, or I can be more formal, and I can say other factors held constant. And so that opens the door for us to consider a richer demand function. Basically, I mean, it's correct to say that if you vary the price of a product, the quantity that you're going to sell is going to vary as well. But that's not the only thing that can affect the willingness of people to buy your product. There are other factors, like how much money they have. So consumers' income. If there are alternatives to your product, how are they priced? If there are other things like how much you spend on advertising and whatnot. So now that brings us to a general form of the demand function, which looks something like this. Quantity demanded will be the function of things like the price of your product, price of related products, income, and then I have another variable for all other things. For Q is our quantity demanded, the amount will be able to sell. is the price of the product, just like for ER would be prices of related products. I is going to be consumer's income. Usually we will look at the representative, like average consumer in the market. And age, placeholder for any other factor you can think of. Advertising expenses, consumers' preferences, consumers' expectations about the future, anything that can potentially affect the demand for the product. Okay, and so one would say that the law of demand requires a negative sloping curve. What we mean is that if we fix all the other prices, if we fix the income, if we fix all the other factors, the relationship between these two has to be negative. But then somewhere in the background, there are all these other things that potentially affect how much buyers will be willing to buy at in terms of the price. So, two things we need to discuss before we look into demand estimation. First of all, how your demand is affected by related products, and second, how your demand is affected by income. This is where things get interesting. Can I raise this? So now, when I change the price, I'm basically jumping from one point of the demand curve to another point in the demand curve. When I change something about factors other than the own price of the product, I'm going to shift the whole curve. So we'll do a little bit of that shifting. Related products. Generally, we can think about two kinds of related products. Products that you can consume along with the product in question, and products that you can consume instead. The first ones are called complements. And notice the E in the middle button I. Complements, complementary goods. Consume with the product. And then there are goods that are called substitutes. Instead. Let's start with substitutes. I tend to memorize one thing for one of the products because it's like left and right, up and down, not to get confused. You memorize it one way, and then you can just mentally flip the right thing once you do something for the opposite case. So substitutes, think about commodities like wheat and corn. Like if you're buying, I'm going to speculate here, I don't know much about farming, but if you're buying wheat for your livestock, maybe you sometimes switch to corn if corn is cheaper, maybe sometimes switch to wheat if wheat is cheaper. To a certain extent, there are substitutes. Corn, as an example. And so, suppose we're looking at the market for wheat here, and I'm going to erase the numbers because we don't need the numbers anymore. What happens to the demand of wheat when corn prices increase? Corn is a substitute. Corn is now more expensive, so at least some consumers, maybe some chickens, will switch to wheat, right? Because corn is now relatively more expensive compared to wheat. So that means that your demand for wheat is going to increase when corn becomes more expensive. But what it means for the demand to increase is that your whole curve is going to shift, no matter what the price is. If the price for wheat was low, people will be demanding more and livestock. If the price of wheat is high, the demand is going to be higher. So your demand is going to shift to the right. No matter what price level I'm aiming at, once the demand has to increase because the substitute is more expensive. And so I'm going to write it down once. If the price of the substitute increases, demand for the product has to increase. And if you want additional emphasis, you could say it has to increase at all prices. It doesn't matter what the price is, the demand is going to shift to the right. Now,
what about cases where it's just catching up?
in what sense?
Well, you said it has to shift to the right. Well, if your in your example, wheat is cheaper than corn today. What if corn suddenly becomes cheaper than wheat?
If corn, so
if the price increases to one, it's going to, I understand they're going to be inverse of each other.
right. So I mean, I'm not going much into detail at this point. So what I'm trying to describe here is kind of the first round effect, right? Kind of the initial reaction of markets to changes in prices. Because I mean, the good way to think about markets is markets are trying to achieve equilibrium in all markets at once. So we don't know if they're actually in equilibrium or not. But if something changes in one market, well, there's going to be a constant back and forth, constant reaction. Here, we're kind of trying to just pull out the first initial reaction of the other market to the change in the corn prices. There is a richer picture, there is a more complicated picture that will, like, you can write an equation for that dependence and then kind of solve for the equilibrium. We're looking at just the basic response. If you expect corn prices to increase, you should expect demand for wheat to go up. You should expect wheat prices to ultimately catch up as well. But my emphasis here is that the whole curve is going to shift. Probably the price is going to increase if supply stays the same. But the talk is not about the equilibrium. We'll focus on the demand side only, just to understand the demand side. For complements, I'm not going to draw a new picture because you can guess what's going to happen, right? If the price of a complement increase and goes down. So say you run a bakery, buy flour, so your flour demand is ultimately your wheat demand, and sugar prices go up. You'll buy less flour, you'll demand less wheat. So with higher sugar prices, demand for wheat has to shift to the left. For me, it will be easier to just reverse the arrow. For you, you'll probably have to draw the graph, but the idea is exactly the same. Similarly, you can say what were to happen were what would happen were the prices to go in the opposite direction. If the price were to decrease for a substitute, demand is going to decrease. If the price were to decrease for a complement, demand is going to increase. So it's all movements left and right, depending on the prices of complement substitutes.
You're saying if the price of the complement increases, demand for the original product goes down.
Yes.
With it in relation.
Yes. If sugar is more expensive, you would want to be buying less flour. And so your demand for wheat is going to be lower. Okay, that's one part of the story. And the second part of the story What about consumers' income? Turns out, with respect to consumer income, we pretty much have two categories as well, and things roughly look exactly the same way, but I just need to spell it out. We have goods that are called normal goods, and we also have goods that are called inferior goods. And the rule here is as follows. If your income as a consumer increases, your demand for normal goods is going to go up. So normal goods follow the income. You become relatively more wealthy, people demand more of a normal good. So the same picture here. Higher demand for higher levels of income. Again, there is no variable for income on the graph, so we need to introduce it by saying, well, if in the background the income decreases, you're gonna demand more. For inferior goods, and by the way, there is no negative connotation to inferior. It's just a term to say, well, this is a good for which demand, income and demand go in opposite directions. Inferior good, increase in income. Demand goes down. You demand something less because you become wealthier.
So that would be like the left inward.
Yeah, let's draw it for once. You have a demand, one on the bottom, price on top, income increases, or demand goes this way. For each price, you demand less of it.
McDonald's,
Yes, McDonald's.
whenever the economy tanks, McDonald's revenue does better. Because it's considered an inferior good for food. Because people aren't going to a steakhouse, they're getting a Big Mac.
Okay, that's a good example. But then you can also think about stranger examples like, say, if you're a college student, what about a used car? Would it be an inferior good or a normal good for college students? Probably normal good,
Yep.
right? A better alternative to bike school. If you're a young professional, probably your used car will become an inferior good for you now, and a new car will become normal good. Buying business class for anybody is normal good. If you're, say, a CEO of a Fortune 500 company, maybe flying business class is an inferior good for you because you can be flying on your own jet. So it's all relative. And I mean, for most people, you can clearly label where that's going to fall. But strictly speaking, once you reach a certain level of income, some things that used to be normal will suddenly become inferior to you. Like maybe now I'm buying Hy-Vee pasta, and then I'm going to switch to Italian pasta from Italy, from actual Italy. And then I'm going to switch to eating out pasta in the restaurant and not cooking for myself as in a little bit. This is how it works. Sometimes it's inferior, sometimes it's normal. But then when we're looking at markets, we can kind of average those effects out and say what on average that product is going to be given the particular market. What it is for most people, like McDonald's for most people is probably an inferior good, even if a lot of people like it. Again, nothing about the quality of the product, just where it stands on your like food preference, where you put it there relative to other alternatives that you have, without any associations with a good product versus bad product, just where it falls. Okay. That's income, advertising, and everything else. You can probably think about how that will affect your demand, but there is no income and related products. It's kind of general to any demand you think about. Everything else is market specific, so we don't have any general things to say about things. Now, what we need to do is we need to shape this general demand function that we were looking at previously. Remember I said, well, going to demand that for alternatively sales, because what you really observe is sales in a particular market. You don't observe this whole thing. You only observe those that correspond to the position of the demand in different points of time, or the position of the demand in different related markets, where that demand meets supply. You only observe a data point in the form of that was the price for the day, and this is how many units were sold today. You don't see all the possible prices and all the possible quantities. So you need to infer that information from this minimum that you have. And so you need to make this assumption that, well, something is stable. Either you're looking at different regions, but you believe that the demand function is the same. It's just regions differ by how much income people have in those regions, and maybe differs by preferences. But then you can still kind of find the general relationship between price and quantity demanded. Or you're looking at one and the same market day in, day out, and you're just going to say that that demand function is still going to be stable, and you can use sort data to try to estimate it. So it's kind of, the problem here is the data we have is not really sufficient to say something meaningful, but we still need to say something. And so we have this function, price of related products, income, other things. And what we will try to do today, we will try to give this function in the simplest shape possible. It's going to be a linear relationship with respect to all variables. So we will say that your demand or your sales is some constant term of some coefficient times the price of the product, other coefficient times the price of another product of related goods, third coefficient times your income, plus the fourth coefficient times whatever other factor you might have in under consideration. So what this model assumes, this is kind of the simplest starting point that you can think about. This model assumes that, well, first of all these factors impact the sales. And second, that all these factors kind of work out their way in isolation. So price of the product has a linear, isolate impact on your sales. It does not interfere, the price of your product does not interfere with the price of the product, say, your competitors charge, which is not entirely true. But again, it's the first approximation, this is a starting point. And then, say, the amount of advertising it has an isolated independent effect on the sales. The incomes of the people have an isolated independent effect on the sales. Maybe it's not a great model at all, and we'll see in our example how it performs. But the basic idea is, well, we have all the possible factors, so let's start with linear. And then you can go into various complications, and your textbook talks about logarithmic transformations and whatnot. We're not going to get to that point. I want you to understand the basics and then see that, well, you can complicate it a lot, and maybe there's going to be an advantage to it, but no, this would be good enough. But what we're going to start with is just this part of the relationship. It's really, the starting point would be just a linear relationship between two variables, quantity and price. So this is the first model that we'll try to estimate. And to do so, you could go to Canvas and you can see the data set that I have prepared for you. There's a handout that has a checklist of things that you need to do if you want to try to estimate a model like that. And I'll first you can copy all the numbers into your own spreadsheet and work them out along with me. Alternatively, you can just stay in that Excel spreadsheet that I shared with you, and things will appear on your screen as I'm doing that. I'm going to do both. I'm going to show you how to do it. You can either follow me on the screen or you can. if there are stairs, I'll write one. Thank you. All right, we're able to access this file. You won't be able to manipulate it. It's you only copy the data and start your own. We will need to use both spreadsheets and Excel today, or if you're using Excel, you can just stick with Excel because spreadsheets don't offer all the okay. What we're trying to do, we have this data set for 14 sales regions, so it's like 14 separate markets. And in each region, I think it's a company that sells paints. So we see how much paint was sold, what the selling price was, and there are some additional attributes like how much we spend on advertising, how much the competitors charge for their paint, and I guess it's like the average income of the consumer in that particular market. Okay, so 5 different variables. Questions? Do you have questions? No, we're good?
No, I'm good.
Okay. All right, so recall what we're trying to do here. We're trying to see whether there is a linear relationship between Y in our sales and the price at which we're selling the product. The first thing that we need to do if we're trying to establish whether there is a linear relationship, we need to grab things. So with 2 variables, it's fairly easy. I'm just going to select the 2 columns in this table that correspond to variables, and I'm going to insert a chart. And the chart is going to be the box plot, sorry, scatter plot, right? So it shows sales on the bottom, price at the top, price on the bottom. This is bad. From the economist perspective, it's really, no, it's not really bad. It's okay because it's showing you the price on the vertical axis and constant on the horizontal axis, just like you want it from the economist perspective. But we're going to trip at one point, and I'm going to show you where it's going to trip. First of all, let's do one thing. Let's scale it up so that it doesn't look that bad. So I'm going to say that the vertical axis has to have a minimum of 10 and maximum value of 20. Like this, right? So we have a cloud of observations. And so now we need to grab, just visually evaluate the cloud of observations, and you need to decide whether it looks like there's a linear relationship there, whether we can kind of pierce it with a straight line, and it will look like those dots, your observations, are very close to that line or not. Does it look like it or not? It's kind of stretched out from top left to bottom right. So it's not like a perfectly great relationship, but at least it's promising. If you look at the second tab in the file that I'm sharing with you, there are examples of how different relationships look like. What we're going for, our dream, would be a cloud that looks like this. It's like a straight line, and all the observations go on a straight line. And so that would be the best. The clouds where things are more or less all over the place, they suggest that there is no linear relationship whatsoever. And so that's kind of bad. But also, we can have situations when there is some kind of regularity, but that regularity is not linear. And by the way, this picture, I think, is from Wikipedia. So it's really helpful, I think, because you can see that, well, if you want to describe this relationship, you can probably describe it with some kind of linear function. But we're attempting to just use a straight line to describe what's going on between price and quantity. And so for cases like this, something else will describe things well, but not a straight line. And so we have this measure for the strength of linear relationship, which is called correlation, right? Anyone, what values can correlation take? Very 1 to 1. So we have correlation that places between -1 to 1. You don't need to know how it's calculated, you just need to know how to calculate that. And what's important is correlation close to 0 means no linear relationship. And I'm going to emphasize linear here, because in the silly Wikipedia examples here, clearly there is some relationship between the variables on this graph, but it's not a linear one, and so it's going to give you a correlation of 0. Clearly there's some kind of relationship here, but the correlation is still going to be 0. So 0 correlation simply says that linear function should not be used. Maybe there is something else. Maybe there is no relationship whatsoever. We can't distinguish between these two situations, but it's linear. And then correlations close to 1 say that things are lying on one and the same line with a positive slope. Correlation close to -1 means things are on one and the same line with a negative slope. And then the closer you are to 1 or -1, the closer your data points to a straight line. And our goal is to find that straight line. So aim at -1 or 1. Let's take the next step. Let's calculate, let's go back to our data and let's calculate that correlation. We can do it at least 2 different ways. For once, if you look at my file here, there is what's called the correlation function. So you can simply type equals correl, and then you just need to highlight the 2 columns that you're using for 2 variables. You can see it. I don't know. Right there on top, that's the formula window. This is where I type in my stuff for Google spreadsheets to execute. That's the formula repeated. And then selecting the 2 ranges, one range for sales and the other range for prices. If you hit enter, it should give you a number between -1 and 1. And that number is -711. So what can we say about this? First of all, good news is that this number is negative. You get the number? The number being negative suggests that the relationship is going to be negative, which is what we want because we want the law of the unfold. If we get a positive relationship, that's going to suggest something strange in our model. We need to investigate more. And second, if it's at 71, it's not super strong, but it's strong enough. If this value was, I don't know, rule of thumb, maybe 30%, if it's below 30%, that's going to be a weak link, a weak relationship. But right now, we're looking at very strong relationships. And then, finally, what we need to do is we need to find an equation. So basically, there is an algorithm that fixes the coefficients for the intercept and the slope, so that your line is going to be the line of the best fit in the sense that it gets as close as possible to the observed points in the data set. I'm not going to go into details exactly what that means. But basically, I mean, if you think about what that line is going to be, if I drew a line like this, probably I'm not going to get close enough to most points. So, I mean, follow your intuition. It has to be running somewhere through it. Good news, in Google Spreadsheets, you can just say, edit chart, and then customize, and in the legend, no, sorry, in the series, you can say trend line. By definition, or rather by default, it gives you a linear trend line. This is what we're going for, linear trend line. This is what we're trying, this is how we're going to be predicting that. And then if you go a little bit down, it also says label use equation, and it also says show R squared.
How did you get to that editor?
There are these 3 dots.
The 3 dots. Okay.
Okay, so pressing 3 dots, edit chart, and then in customize goes to the series, add trend line, and the equation. You can do a ton of things with that. What is this value of R squared for? Let's look at that first. So we calculated the correlation. This is just correlation squared. So if you take correlation is negative 0.7, our square from L to B 0.1. The reason that they show you correlation squared is because it has a meaning to it. It simply says that roughly 50% of the variation in sales can be explained by the relationship between sales and price. 50.5% of variation in sales can be explained by volume. Basically, our original question is like, why are sales sometimes high and sometimes low? Do prices of the product have something to do with sales? And the answer is, well, the relationship between prices and quantity can explain about half of the variation in quantity. We can. This is how much spread in the data along the y-axis we can explain. Okay, don't copy that equation yet, because that equation is unfortunately incorrect. And we'll see why in just a minute. Now, let's find the coefficients of this line by using the built-in formulas. So I'm going to go back to my spreadsheet, and I'm going to calculate the slope and the intercept using the formula. So I'm going to type in equal, then I'm going to say slope, and then see it starts a function that's called slope, and that function has two inputs. You need to say what the range for the predicted stuff is going to be. So that would be sales, so sales have to come first, and then you need to put a comma and say what the range of the prices goes. Prices have to go second. Whatever you're trying to predict is going to go first. Sales goes first, and then comma, prices go second. Then I'm going to hit enter, and it's going to give me the slope. For the intercept, I'm going to say intercept, and again, sales first, prices second. It calculated these two numbers that I need from my linear equation. But these two numbers are not the same as the numbers that appear here. Because spreadsheets always treats
Sales go first and then price range, your sales range, and then your price range.
So calculated regression numbers for sales on the price. So I did it on purpose, and the learning experience here is that if you want to represent the demand function, I want the price to have to be on the vertical axis and sales to be on the horizontal axis. If you want to use the shortcut of finding the trend line from the data, you need to ensure that your dependent variable is here. So now we're going to perform the second simple trick. We're going to go back to editing the chart. And in the setup, And you need to check against the analysis of that. At this moment. And then what was going to happen? If you add this analysis tool back, something says there's a new icon on the right here. It's there's a data analysis tab. File, options, add ease, go on the file, add the tool file, presentation.
I'm sorry, could you do it one more time?
Sure. File, options, and then toward the bottom on the left, there is the add ease tab. On the very bottom, there's go tab. And then you they really tied it well. They really
Did you find it? Has it like, it has analysis tools right there, other data, like this. So go to data. Oh, there, okay. Yeah, and then you just add it there. It's
you raise your hand if you're able to find it.
I was not.
If you aren't, can you move closer to somebody who has that on the screen, or just follow me here. Okay. So now what I'm going to do next is I'm going to keep that data analysis tool, and each offers you a ton of stuff here. You need to select regression, and it shows you this window where you will never mess this up because it says, well, what are you trying to predict? What are you going to use to predict that? And then there are some special settings. And so I'm going to run it one more time with you because this output of the regression feature in Excel is more meaningful, has way more information. Let's see here. So for the output range, I'm going to again select my sales and I'm going to include the label. For the input range, I'm going to select my seller price and again I'm going to include the label. Okay. Now, because I included the labels, I'm going to put a check mark against the labels. We'll create the first entry in the column of the label. And then I'm also going to say, give me the confidence level 95%, whatever that means for now. And for the output range, I'm going to just select some cells below my data set. Ready? And then I'm going to cross my fingers because with Excel, I always feel like something might go wrong. I really like this, which is better for minor tasks. And then, okay. And then if summary output shows up, that means we're running. Let's see here. Can you see it better this way? Mm-hmm. You should be getting the same thing on your screen if you're able to get as far as I got. First of all, kind of the first reading that I looked at, R squared right here is exactly the same R squared that we had before. 15.5%, that's basically the quality of the model. How much explanatory power that is. Okay. So we've seen that before. But then another thing that you need to look at is significant number right here. This is a probability measure. So you want it to be as close to 0 as possible. If it's closer to 1, that means that your model is basically bad. Significance close to 0 means that your model is meaningful. Maybe it's not the best one, but at least it's saying something. And then, if you look at the coefficients, first thing that I want you to notice that for a model with just one variable, we're just looking at the price. The p-value is going to be the same as the significance. Basically, your model with one explanatory variable is only going to be good, but the selling price is a good explanation of what happened to your sales. Let's make it a little even larger. So what's going on here? The first row here has four coefficients, just like we calculated for the model. 402.3, negative 14, roughly negative 14.5. This is what we're seeing right here, right? And so the ultimate idea here is that those coefficients are not set in stone. We're not getting a whole picture. We're not getting exactly all possible observations there could be. We're only getting a sample from kind of a larger population. So these two numbers, 402 and negative 14.5, are our best guesses about what the actual values are. Our guess would be the better, the more observations that we have. Here we only have 14 observations. Right, so it's pretty much a wild guess to a certain extent. And so what the Excel function does for us, it kind of puts that guess into an interval framework. It says, well, if you want to point guess about what the slope and the intercept are, the best thing that we can say is that the intercept is going to be 402, the slope is going to be negative 14.5. But then we need to look at the interval. And so Excel is saying that very likely your actual value of the intercept is going to be between roughly 265 and 540. So 402, but actually between 265 and 540. And for negative 14.5, our best guess is negative 14.5. But if we want to say with confidence, we can just say that it's very likely it's going to be between negative 23.5 and negative 5.5, right? So we can have like a point estimate, a point guess about what the best value is for the slope. But we can also say an interval estimate, where the actual value for the demand is likely to fall. Because while we don't have all the data, we just have 14 observations. So we're making a guess based on 14 observations. And so our model is good in this interval for the intercept. Forget about the slope. I mean, slope is just there because we need it. If this interval contains 0, that's bad. Because it might mean that in reality, there could be a 0 relationship. Like that the actual value of this parameter is 0. And so price has no effect on your sales, and your sales are varying from market to market for a reason different than the price. Okay? So just remember that if you're looking at the coefficient for something that you're using, that you're trying to use to explain your sales, that coefficient has to be either the interval for that coefficient either has to be always in the negative or always in the positive. If it overlaps with 0, that means that it could be in reality that this true coefficient is 0, and then your model does not do any explanation at all. Because it says your price can possibly have 0 effect on your sales. In this story, it's not the case. So it's good.
Why does Excel give you two ranges simultaneously?
I think it's a glitch. Because it does that, yeah, it does it twice. One and the same thing twice. All right. Questions about this? Well, this is a linear regression. Who has seen something like that before? Now let's forget that, but we need to do something more complicated this time because we can go back to our data set, and our data set actually contains more stuff than just the selling price. So far we've fit this model, sales versus the price. The model has like 15.5% explanatory power. Not good, but not bad. Just okay. So let's see if we can get more explanatory power if we try to fit in a model that also incorporates advertisements, prices of the competitor, and disposable income. Before we run the second regression, we need to do the check, the check that we did before running the first regression. Is it meaningful to consider a linear model to begin with? And to do so, we looked at the scatter plotted correlations in the previous round, right? We looked at the correlation between sales and price. Now, I'm not going to do all the scatter plots, because it's going to take a lot of time. I'm just going to look at the correlation patterns. So here's how we're going to do it. I'm going to move a little bit to the right of my data set, and I'm going to, let's see here. press data analysis, but now instead of selecting regression, I'm going to select correlation. Okay, and for the input range, I'm going to select everything excluding the sales region, because the sales region is there just to kind of give you the idea of what we're dealing with. But everything from sales all the way down to the disposable income, basically the whole block of numbers with labels in the first row. And we're looking at columns as so for the input range, just select your whole data set, excluding the first column where it just has the IP numbers for each. Yeah.
You kept the titles too?
Yeah, because then you can say labels in the first row. And then it's going to give you the titles instead of saying variable 1, variable 2, variable 3, and so on. Okay. And for the output range, I'm going to select some point, some cell, just slightly to the right. Because that's where I have space. Okay, can I press OK? All right. And so there we go. It gives me, if everything's performed as expected, it gives me a table of correlations. So it basically, it takes all the variables that there are and treats them the same way. It doesn't distinguish between dependent and independent variables. Okay. And so clearly, these ones are just because it's the correlation of the variables itself. It's always going to show up as 1. So ignore those ones that are not informative here. The first column is the correlation of your explanatory variables to the sales. This is what we care about. And you can see that this negative 771, 7103 is this negative 711 that we calculated when we tried to fit in the simple model of the previous term. So this is that correlation.
Can you say that again?
It is negative 0.71. We just calculated it before we ran the previous model, right? It's the same number. So it's there to just boost our confidence that what we're doing is the same as what we did before. Okay, so so what do we want here? First of all, we want all these numbers in the first column to be as far away from 0 as possible. If we're trying to fit in a linear model, we want actually a linear relationship between our sales and our explanatory variables. So 0.7 for the selling price, that checks. 0.45 between sales and advertisement. So 0.17, that's going to be bad. And 0.39, again, so. Right?
So you want it to say you want it to be closer to 1?
Closer to 1 or negative 1. Basically, that will indicate that there is some linearity going on, because we're looking at the linearity between sales, selling price, sales and prices of competitors, and sales and everything else, right? So we want as much linear relationship, as strong linear relationship as we can get. When we're looking at these numbers, it's the other way around. If we get something close to 1 or negative 1 here, that's going to be problematic. Because this is what's called multi-linearity. And so this is what's going to conceive our model. And it's going to be problematic in the following sense. Suppose I'm going to look at an extreme example. Suppose that your competitors in every region match your price exactly. Your price and your competitor's price is exactly the same number. The correlation between the two is then going to be 1, which means that your competitor's price, when included as an additional explanatory variable, carries 0 additional information. So high correlation between your explanatory variables means that you can basically throw it out and you don't lose any information at all. If I know that the correlation between my price and my competitor's price is 1, I can erase all the competitors' prices from the data set and I don't lose any information because I know that I can reconstruct them by looking at the final price. So if there is strong relationship between, say, between advertising and the selling price, I can kind of recap advertising from the selling prices. Selling price carries all that information that advertising carries too. And so advertising on top of the selling price will not contribute much to my explanatory power of the model. This is why we want these numbers to be away from zero. So these look suspicious, these look suspicious. Be close to zero, be away from one. These two look suspicious, but I'm not going to run into a formal test of how to check that. Just be aware that high correlations here means that your independent variables are kind of interchangeable, and you should not be using both of them in the same model. All right. And so once we perform this test, let's go ahead. Let's go back to the data analysis. Keep regression as well. One more time. Now for the input range, we want the sales again. So I'm going to keep the input range intact. It usually keeps your previous settings in it. For the input X range, I'm going to delete it, and I'm going to highlight selling price, promotion, competitor's price, and disposable income. So all the four columns of data that I have. And again, I want label the confidence level. And finally, for the output range, I'm going to go slightly below, just not to overlap with the output of the previous effect, so that we can compare it back to that. Okay. So I'm going to ask it to calculate another regression. Now it's going to be a multiple regression, and I'm going to spit it out here. You know. Okay. Crossing the fingers. Summary output. Okay, we're good. Let's see what happens here. Again, what are the checkpoints when we get the output for the regression? First of all, R squared. How are we doing here? A little better, but not too much. Right? So compared to the original model, we gained what 1.2% in explanatory power. That's very little. Your R squared, if you throw in additional variables, your R squared is never going to go down. But if you throw in additional variables that are kind of crappy, as in this example, as it will turn out, your R squared is not going to increase that much. Basically, price alone does almost as good a job as price plus advertising plus price of the competitors plus anything. So that means that if your explanatory power is only increased by very little, that means a lot of the coefficients will likely be zero. Let's see how. Okay, so first check R squared, second check significance. That probability is 12.5%. We want that probability to be rule of thumb under 5%. Significance of 12.5% means likely it is that model. Let's see where that model is exactly that. So we have this new coefficients. You can see that coefficients are kind of similar to the intercept and the selling price. And then for promotion, competitor's price and disposable income, those coefficients are somewhat close to zero. Coefficients are close to zero, that should raise around 5. And this is where I like looking at the intervals, because intervals are make value. For the selling price, the interval overlaps with 0. Its left tail is negative, its right tail is positive. So it could be that the true value for the selling price of this model is 0. These intervals also contain 0. The next interval contains 0, and the last interval contains 0. So none of the 4 primary are statistically significant. It could be, according to this model, it is not unlikely that the true relationship is such that they are not affected by your price, not affected by advertisement, not affected by the price of the competitors, and not affected by income. We don't know if it's true or not, because we don't know the true values. But the model says this is not impossible. And because this is not impossible, this is a bad model, because it says potentially there is no relationship between the variables we're trying to use to explain the relationship and the variable basis. So that's bad news. But, well, we need to deal with bad news somehow. And the usual story here is elimination. we need to throw away variables that perform poorly, but we can't throw them all away at once because in this story, all variables perform poorly. So we need to do it one at a time. And the usual thing is to look at the p-value and find the one with the highest p-value, the closest one, which means that it's closest to zero statistical speed. This interval is centered almost near zero. So we're going to get rid of competitors' prices. Looks like competitors' prices are contributing less than everybody else does in terms of the exponential power. So now this is where things get a little tricky. I need to go back. I need to run a new regression, but it won't let me run a new regression if I don't have a continuous data set. So I can't just tell it to use these two columns and the last column to explain things. I need to actually get rid of the competitor's price so that I have three columns side by side for it to be able to do a correct for me. Otherwise, it will give you an error. So I'm going to copy my data set. I'm going to print it down. Okay. And then I'm going to take the disposable income, copy the disposable income, and just throw it over the competitor's price. Because I need these three columns side by side. And then I'm going to call the regression one more time. And I'm going to say for the input range, I want the sales, input X range. I want selling price, promotional expenditures, and disposable income, but not the competitor's prices, right? So I'm choosing only three columns here. Same label, same confidence level, and for the output range, something below right here. And then press OK.
What did you pick for your X range?
For the X range, I picked these three columns: selling price, promotional expenditures, and disposable income. We decided to get rid of the price of the competitor. They don't think we need it.
So did you keep the original data set for the first part of the regression then?
You can do that. It's the same number. Yeah. I sort of copied, I created a new table and I used the column from the new table, but if you keep the original Y range, everything's going to be the same because it's the same numbers.
Okay.
Great. You're still with me? Okay. Not much left. We're just getting rid of the trash. And in the data. Metaphorically speaking, of course.
In drug trials, it's really bad to throw out data, you don't like just throwing it out there.
Yeah. But then, so look at the R squared. R squared was something like what? 518, and now it's 5179. If you throw the trash away from the house, the value of the house does not change much. Right? We threw away those competitors' prices, but our explanatory power did not increase much because in the previous model, it's just that the value of the parameter is going to be zero, or likely to be zero, near zero. So you're throwing out a variable that has potentially zero connection to your sales. Hopefully in real data, because I don't think that this is real data. Hopefully in real data, your competitors' prices explain something. Your more consumers probably weighed at the options of buying from the courses from whatever. Okay. But so this is a nice feature of this model. To throw away something that seems to be unimportant and your explanatory power does not affect much by it. What about the significance? We're at 5%, but we're above 5%. So we're kind of like borderline not passing that test. What about our coefficients? Okay, selling price back to being significant because zero is not in the interval number. Right? We want selling price to be significant. We can sacrifice everything else, but if your sales do not depend on your selling price, what kind of business are we having? Promotions, okay, zero is still there. Disposable income, zero is still there. still the same problem, right? We eliminated one variable. One variable is now significant, but the remaining two are not significant any longer. Question?
You can look at just the p-value for that as well, right?
Yeah, it's all the same, but yeah, p-value, if the p-value is going to be above 5%, then 0 is going to be there. So everything that does not contain 0 to 95% interval will correspond to p-value less than 5%. But I like this is more kind of visual, because you can see that 0 is there. 0 is in between these two numbers. So it would be that the true coefficient for disposable income is 0. And so again, I need somebody to walk the plank to simplify the model. And if you compare the p-values, disposable income has the highest p-value of the remaining ones. We're going to get rid of it next. And so there's one iteration remaining, because if we only have 2, and then it turns out that one of the 2 is insignificant, then we'll go back to the original one right there. But we just need to run one more regression. Okay. So what are we going to do next then? Going back to this data set. So now I only care about the selling price and promotional expenditures. Data analysis, regression, save input Y range. For the output, for the input X range, I need to get rid of the disposable income, just selling price and advertising. Labels, confidence level, and for the output range, I'm going to put it here. Okay. This is our last regression. Okay, so we threw away income. R squared has gone down 7/1000. So we lost a little bit of exponential power. So the income did contribute almost slightly. So we got rid of it. Our value of R squared has decreased. But a very small decrease, so we should very much show that. Let's see here. Significance. Significantly improve the significance. So we should be happier about this model as compared to the previous model. But then if we look at the intervals, okay, so the selling price again does not contain 0, which is something that we need to hold on to really. Advertising, potentially 0, which means potentially we'll need to let the advertising grow. Potentially. If you compare expenses do not contribute to our sales and white collar, right? And so here, well, we have a model that is overall significant, but we have a variable whose coefficient might be 0 in reality. And so then it brings us to this kind of unkind trade-off. You can use the original model that focuses on price only, and remember it has exponential power. Or you can have this model that says your sales are what? 434 minus 9 times the price minus 0.08 times advertising. We actually have to let advertising go because that coefficient is negative here. That means that what they spend on advertising contributes to fewer sales. People hate our ads. But of course, they can argue maybe it's actually positive, maybe it's actually 0. Don't find us right away. So this model is explanatory power. What is it? 51.0%. So we're getting 0.5% by throwing ads into the story. But the price that we're paying is that this coefficient is actually very close to 0. So it's kind of there, but kind of not there at all. So there's nothing to be happy about in this story, unfortunately. The multiple, any kind of linear models that have things beyond the price, they fail on us. They produce parameters that are not statistically significant. So it might be that the true relationship here is that advertising doesn't have a significant impact on our sales, and so sticking to the original price. Simple does not necessarily mean bad. Simple would be as good as a more complicated story. What is the moral of our actions here? We collect all the data possible. We try to utilize all the data possible in our model, at least in this linear version of our model. But then, if some data seems to be irrelevant, well, get rid of it. It's not contributing much to the story, and it just keeps things more immersive. Ultimately, the thing that we really care about is statistically significant negative coefficient in front of the price, and other things will, if possible, but if not, then no.
Where is explanatory power? You want that closer to 1 if you can.
Yeah.
If the data is better.
Yes, of course. And that power is always going to increase if you throw in additional variables, even if that data is unrelated to what is going on. But it's not going to increase by much if the relationship is very weak.
But if the data is really strong, it will add and bring you a lot
Yes,
closer to
yes,
1.
yes. If there is really something that we can uncover, it's going to go up quite a lot. Yeah, multiple regression is kind of potentially more powerful if we can find the right additional variables. So you want to do the last 5 or 10 minutes. We need to talk a little bit about elasticity. Again, going back to the homework on the previous book. So say you have this model now. I'm gonna stick to the more complicated one, although I don't have good reason to do so.
You said you're going to stick to the more complicated, even though you don't have good reasons.
Yeah, I'm saying that there is no good reason because the more complicated one gets only 0.5% more of the explanatory power, and this coefficient is actually not statistically significant. So you have to be very cautious using that coefficient.
But why would you then?
Just because I want to talk about an additional concept that I want to show how it can be applied. All right. So we need to talk about elasticity, and we're going to briefly talk about it. My undergraduate students gave this concept that they took a test today, and I think elasticity is kind of the low point of undergraduate economics. But we need to talk about it because it's very useful. And once you overcome this resistance that elasticity presents, you will see how useful it is. So we have this model. What is it? 434 minus 15.9 price minus 0.08 times advertising, right? This is our model. Let's for a moment forget that it's not a great model. Let's think about it as a good model. So what does it say? It says that these two variables are within my control. I can adjust prices and I can adjust advertising expenses, and they would independently affect my sales. And so now I want to calculate the effect on my sales, but I don't want to calculate that effect in quantities. I want to calculate it in percentage terms. So elasticity is simply transitioning from prices measured in dollars and quantities measured in units to prices and quantities measured in percentage terms. Just because percentages, when it comes to prices, is a little bit more meaningful. If I told you price increased by $5, you would say, well, what was the original price? For an airplane ticket, a $5 change in price is nothing. It would not affect our sales. Gas prices increased by $5, you will look suspicious then. So instead of saying price increased by $5, usually I would say something like price increased 5%, because that's meaningful. 5% is a meaningful change because I don't need to give you the base. And so basically, elasticity is just going away from this kind of slopes. What is the unit of measure here? For what? Means that for every $1 increase in price, your sales will drop by 16 units. Right? So that's units per dollar. $1 change in price will result in 16 units change in your sales, predicted sales. What is the mirror here? Units per dollar too. $1 change in your advertising will increase your sales by 0.08 of a unit. So you need to spend another $100 to sell 8 more units. Or, sorry, you need to not spend another $100 because this
Negative, yeah.
tricks me here.
Okay.
That this is not intuitive. This is not how advertising should work, right? But like every $100 you throw into the advertising hole reduces your sales by 8. This is the correct. Okay, so again, it's units per dollar. So now for elasticities, we want to go into unitless measures. What we're going to do, calculate elasticity. And in this example, we're going to have two elasticities. One is going to be the price elasticity of demand. So that's going to be the elasticity with respect to our price. So sometimes also called own price elasticity. It's going to be the slope in front of the price. Slope for price. We need to multiply it by price and divide it by quantity. Times the ratio of price over quantity. And then we also can have advertising elasticity. Going to be slope for advertising and the advertising value over the quantity again. So now I need to give you some data so you can deal with it. And I think that data is on the reverse page of your account. Let's plug in the numbers. Suppose I told you that this price was $16 and we actually spent $110 on advertising. First of all, if you plug in the price instead of P and advertising instead of the advertising line instead of A, you can calculate the expected sales, the predicted sales, given the price that you set and the amount of money that you're going to spend on ads. Give me that number, please. I don't think I have. Guess they're first. Should be something like 175. Do the calculation.
170.8.
The quantity, the predicted quantity of sales. I mean, what do we need? What do we need a demand function for? We need to understand this relationship so that we can set up the price and decide on other things that are within our control in order to get the right number for the sales. In this story, if this is the relationship that we get, if we were to set the price equal to 16, then $110 in advertising, we should expect to sell roughly 171 units of the product. Right? This is just plugging in the numbers into this linear equation. Now let's plug in the numbers into this equation as well. What is own price elasticity of demand? It's going to be negative 15.9 times the price of 16 and quantity times divided by 170.8. And that equals, go ahead and calculate that number. It has to be 2.4. 1.4, sorry, 1.4, something roughly
1.489.
1.9. Next. Elasticity of advertising. Slope here is negative 0.08 times advertising at 110 divided by quantity 170.8. Okay, that number has to be roughly 0.03. How much?
0.05.
0.05. Okay, negative 0.05. Okay, these are your elasticity numbers. Now, what do they mean here? For each 1% increase in price, your quantity will drop by 1.49%. Let me write it down separately. Price elasticity of negative 1.49, 1% increase in price results in 149% reduction in sales. It plus both quantity, right? And then 1% increase in advertisement gives you a 0.05% reduction in sales. So instead of slopes, we translated that into like percentage slopes. And it's a little bit useful. Because the last thing that we want to answer today, what if we increase the price by 5% from 16 and also at the same time reduce advertising by 20%? Instead of calculating what the new price is going to be, what the new advertising amount is going to be, we can just say each 1% increase in price reduces your quantity by 149%. So 5% increase times negative 149.
7.5.
Negative 7.5%. 5% increase in price will bring your quantity down 7.5%. Elasticity just translates 1% change immediately into another percentage change without having to go back to quantities in units and price of dollars. Similarly, what we say is 20% reduction in advertisement times negative 0.05, probably we get 1% in sales. As a also reminder,
5%.
what?
If you fire them, you get 5% increase.
Probably. Yeah, I'm very skeptical about the advertising industry, but there is a value there, right? And I didn't cook the numbers up just for that point. It's a good industry. All right, I'm going to stop at this point. I just given you a flavor of what elasticity is about. I need to give you more video to support that, so expect that because I know that this is a hard part. But ultimately, it's just talking percent versus percent rather than units versus dollars. That's the whole point. All right, that's all. Thank you.
Do you want our assignments?
Of course.
Are you sure? I think it takes. So, okay, so into that is probably okay.